The James Webb Space Telescope is upsetting the apple cart. All of a sudden we realize that we may have to rewrite all the textbooks about the beginning of the universe.
Astronomy has made amazing strides thanks to the James Webb Space Telescope, which provides a previously unattainable view into the deepest and most remote regions of the cosmos. Scientists and the general public have long been captivated by Pluto, a minor planet, which is the subject of one of the most important and unexpected recent discoveries. What was formerly believed to be a frigid, desolate world at the fringe of our solar system has proven to be considerably more fascinating than initially believed. The James Webb Telescope has uncovered previously undiscovered, startling new information about Pluto that are fundamentally altering our understanding of this far-off planet. Please remember to like and subscribe to our channel before we begin for additional updates. Before being downgraded to a dwarf planet in 2006, Pluto was ranked as the 9th planet in our solar system. Since then, spacecraft like NASA's New Horizons, which made a flyby in 2015, and now the James Webb, which has given us even more knowledge, have contributed significantly to our understanding of Pluto. Prior to the James Webb Telescope's launch, Earth-based telescopes were used for the majority of Pluto studies, although they were limited in their ability to record detail. NASA had long assumed that Pluto was hiding more secrets than it was willing to admit, but what James Webb found dramatically supported those theories. Scientists have been anxious to investigate Pluto's surface, atmosphere, and the hidden intricacies of its moons ever since the James Webb Space Telescope trained its powerful lenses on the planet. By using infrared equipment, the James Webb spacecraft can see characteristics that were previously hidden behind Pluto's clouds and frozen atmosphere. Beyond Pluto's icy, far-off surface, they discovered a much more active and sophisticated structure than they had ever expected. The finding that Pluto appears to have an underground ocean under its ice surface was among the most astounding. It was previously believed that Pluto was a frozen world that was too frigid to support liquid water. Nonetheless, the information gathered by James Webb implies that Pluto's core generates heat that keeps a subterranean ocean liquid. This finding may significantly alter our perception of potential life locations in the cosmos. One of the necessary components of life as we know it is liquid water, and the prospect that Pluto may have subsurface life has rekindled interest in the quest for alien life. The topic of Pluto's subterranean ocean's existence also calls into doubt Pluto's geological processes. Pluto doesn't seem to be a dead planet. Instead, it seems to be experiencing tectonic movements and cryovolcanism, which is volcanic activity that spews ice forms of water, ammonia, or methane instead of molten rock. The discovery by James Webb of what seem to be cryovolcanoes on Pluto's surface raises the possibility that the dwarf planet occasionally sees ice material explode from its innards. Such activity suggests that the globe is far from static, with forces operating under its surface that are always changing its surface. A significant finding from the James Webb observations is the intricate atmosphere around Pluto. Although Pluto's atmosphere was previously identified by the New Horizons mission, significantly more precise details regarding its makeup and characteristics have been revealed by the James Webb Telescope. Despite its thinness, Pluto's atmosphere appears to fluctuate significantly based on where it is in its extended orbit around the Sun. Pluto's atmosphere vaporizes again when it gets closer to the Sun, but it freezes and falls to the surface as it gets further away. Sublimation is a cyclic process that is far more dynamic than previously believed. Furthermore, unexpected gases in Pluto's atmosphere have been discovered by James Webb's infrared capabilities. These gases may include residues of organic molecules that were created by biological or chemical activities in the atmosphere. Pluto's atmosphere contains organic chemicals, which raises more questions about the potential of life on this far-off planet. The basic blocks of life are organic molecules. Although the precise makeup of these substances is still being investigated, their existence begs intriguing questions regarding whether or not rudimentary life forms have ever lived on Pluto. Could life exist in the icy, hostile environment underneath Pluto's surface? Although it is too soon to provide a conclusive response, the finding of organic chemicals raises intriguing possibilities regarding the existence of a subterranean ocean. It has also become clear that Pluto's surface is significantly more diverse than originally thought. High-resolution photos taken by James Webb reveal a very varied terrain. Huge expanses of nitrogen ice blanket Pluto's surface, dotted with water ice mountains and enigmatic red areas that scientists surmise may be tholin deposits, complex organic compounds produced when methane interacts with cosmic rays or ultraviolet light. These tholin deposits may include information on the chemical activities occurring on Pluto, and they may even bear similarities to the primordial chemistry that existed on Earth prior to the emergence of life. Along with these findings, there is now a revived interest in Pluto's moons. It was originally believed that Pluto's biggest moon, Charon, was geologically dormant. James Webb, however, has noticed indications of recent tectonic activity. Large cracks and canyons may be seen on Charon's surface, which suggests that at some point in its past, internal heating may have also occurred there. This begs the issue of whether, like Pluto, Charon may have a subterranean ocean, albeit the evidence is not as strong on this point. However, the prospect that liquid water may be present under the surfaces of both Pluto and its moon has sparked intense astrobiological study in the once peaceful outer regions of the solar system. The orbital dynamics between Pluto's moons and Pluto itself is one of the most mysterious features of Pluto. James Webb's investigations have shed fresh light on the interactions between these moons and Pluto. Some of Pluto's smaller moons, for example, seem to have chaotic orbits, tumbling across space in an unpredictable manner. The intricate gravitational interactions that exist between Pluto and its 5 moons are probably the cause of this. Given that Pluto and its moons are believed to be leftovers of the Kuiper Belt, an area of space populated with frozen bodies left over from the solar system's birth, learning more about the dynamics of these moons might provide important details about the early history of the solar system. What these new findings indicate for the future of space travel is one of the main concerns that emerges from them. Pluto and its moons appear to be much more than just lifeless, frigid remnants of the solar system's ancient past, according to data obtained by the James Webb Telescope. Rather, they are dynamic planets with intricate atmospheres, active geological processes, and perhaps even the conditions required for life. This suggests that comparable surprises may be hiding on other far-off objects in the Kuiper Belt and possibly beyond. Furthermore, the location of potential search sites for extrasolar life are affected by the finding of a subterranean ocean on Pluto. The habitable zone, or the area surrounding a star where liquid water may exist on the surface, is where planets and moons have traditionally been the focus of searches for alien life. However, Pluto is well beyond this zone, yet it appears to contain the parameters essential for liquid water to exist under its surface. This implies that liquid water, and perhaps even life, may be present on other frozen worlds, even ones that are distant from their parent stars. Scientists may now be more inclined to investigate other minor planets and moons in the outer solar system, such Europa, Enceladus, and Triton, which are all believed to contain subterranean seas, in light of the circumstances found on Pluto. These findings have consequences that go well beyond our solar system. Similar things may exist in other solar systems if Pluto, a tiny ice world, can have an active geology, a complex atmosphere, and maybe even an ocean. Pluto lives in the Kuiper Belt, which is only one example of an area of space full with tiny, frozen worlds. There are probably Kuiper Belt-like areas in many more solar systems, and the objects therein may be as active and unexpected as Pluto. One day, the James Webb Space Telescope may find habitable planets around far-off stars thanks to its capacity to look into distant star systems, creating new avenues for the hunt for extrasolar life. The significance of continuing to invest in space exploration and technology is further highlighted by the findings made on Pluto. The most potent space observatory ever constructed, the James Webb Telescope, exemplifies the enormous significance of such endeavors with its capacity to unveil the hidden intricacies of far-off worlds like Pluto. We are continuously reminded that the cosmos is full of surprises and that there is still a great deal we do not know about the worlds around us as we push the boundaries of what we can perceive. Pluto, which was formerly thought of as the planet that was forgotten at the frontier of the solar system, is now the focus of scientific study, serving as a reminder that even the farthest objects in space may provide clues to the answers to the bigger riddles of the universe. The discoveries made concerning Pluto by the James Webb Space Telescope, James Webb, are igniting interest in the solar system's outer regions once again. What used to appear to be a cold, barren planet is now understood to be the product of intricate processes, active geology, and perhaps even the birthplace of life's basic elements. The ramifications of these discoveries, when further study is conducted, might go well beyond Pluto itself. They could have an impact on our knowledge of how planetary systems work, the possible evolution of life, and the locations of analogous occurrences elsewhere in the cosmos. The fact that the recent discoveries on Pluto contradict our long-held beliefs about the circumstances necessary for life is one of their most fascinating features. The habitable zone, the area where liquid water may persist on a planet's surface due to temperate temperatures, has been the main focus of the hunt for life for many years. Pluto appeared to be far beyond of any livable zone as it sat at the icy border of the solar system. The criteria for the hunt for life, however, have changed with the finding of a deep ocean, suggesting that liquid water may survive in even more harsh circumstances than previously believed. Though it may sound like science fiction, there is scientific evidence to support the potential of life on Pluto. If there is an ocean below the surface, it may be protected from the extreme weather on the surface by a thick layer of ice, similar to the seas thought to exist on the moons of Jupiter and Saturn, Europa and Enceladus, respectively. Internal heating processes, such as the remaining heat from Pluto's creation or the gravitational interactions between Pluto and its moons, might keep these seas liquid. These kinds of habitats could offer pockets where life could exist, protected from the intense radiation and cold that characterize the dwarf planet's surface. Apart from the prospects for life, Pluto's intricate atmosphere is gaining a lot of attention. The atmosphere is behaving differently than previously thought according to the James Webb Space Telescope's comprehensive infrared studies. Although methane and carbon monoxide are present in minute amounts in Pluto's atmosphere, the James Webb Space Telescope has found evidence of more sophisticated organic compounds. These molecules may be created by photolysis, the process of sunlight interacting with Pluto's surface ices, or by cosmic rays interacting with Pluto's atmosphere. These substances are interesting because they are frequently intermediates in more sophisticated organic chemistry, the type that might potentially result in nucleotides or amino acids, the building blocks of life. Additionally, these findings imply that Pluto's atmosphere is significantly more dynamic than previously believed. Pluto has dramatic seasonal variations while it travels along its 248-year elliptical orbit. Its atmosphere grows when surface ices sublimate into gas at its closest point to the Sun. This atmosphere condenses and freezes back onto the surface as it gets further away from the Sun. The results of James Webb suggest that these procedures may not be as simple as previously thought. Possibly because to Pluto's distinct geology and interior heat, complicated interactions between the surface and atmosphere appear to be occurring as Pluto advances away from the Sun rather than a progressive loss of atmosphere. These discoveries contribute to the increasing understanding that Pluto is a dynamic planet that is always changing, rather than a straightforward, inert entity. Another topic of significant interest is how Pluto's moons, especially Charon, have shaped the ecosystem around the dwarf planet. With a mass around half that of Pluto, Charon has a strong gravitational pull on its parent planet. This interaction influences Pluto's atmosphere's behavior in addition to causing the tidal heating that might maintain Pluto's interior ocean in a liquid condition. Pluto's atmosphere may be distorted by Charon's gravitational force, which might add to the unusual dynamics that James Webb has seen. Furthermore, Charon itself exhibits surface characteristics that point to a past of tectonic movements and potentially cryovolcanism, indicating signals of geological activity. This begs the issue of whether Charon, too, is capable of supporting a subterranean ocean and what that would entail for the possibility of moons in the outer solar system being habitable. New information about the past of Pluto and Charon has also been made possible by James Webb's investigations of these celestial planets. Pluto's surface is cratered, a sign that it has been hit by debris from the Kuiper Belt, an area beyond Neptune that is home to frozen planets and solar system leftovers from the early era. Nonetheless, several areas of Pluto, including the enormous expanses of nitrogen ice called Sputnik planitia, seem to be quite fresh and have few impact craters. This implies that Pluto has recently resurfaced, most likely as a result of tectonic or cryovolcanic events in the Earth's crust. Likewise, the shattered surface of Charon indicates a past of geological activity and interior heating. These findings suggest that Pluto and its moons are living planets that have changed over billions of years, not ancient artifacts stuck in time. Comprehending Pluto's geological and atmospheric mechanisms is essential to assembling the larger picture of the solar system's genesis and development. One of the biggest objects in the Kuiper Belt, which is believed to have some of the solar system's oldest and most primordial material, is Pluto. Scientists can learn more about the early history of the solar system, including how the planets originated and moved to their present locations, by examining Pluto. New insights into the chemical makeup of Pluto's atmosphere and surface are being offered by the James Webb observations, which may aid scientists in comprehending the mechanisms that form not just Pluto but also other Kuiper Belt objects. It also clarifies the more general issue of how planets and their satellites interact, given the intricate relationship between Pluto, its moons, and the surrounding space environment. For example, Pluto and Charon have a unique gravitational connection in the solar system. Because of its size in comparison to Pluto, Charon and Pluto are frequently referred to as a twin dwarf planet system. Because of their tidal locking, which keeps both bodies facing the same way, the geology and atmospheric dynamics of both are impacted. Scientists are learning more about the formation and evolution of these systems thanks to James Webb studies, and this knowledge may have ramifications for our comprehension of exoplanetary systems. The surprising information from Pluto has caused other ice worlds in the outer solar system to be reassessed. If Pluto, a planet long believed to be lifeless and frigid, can display such intricate activity, imagine what may be occurring on other objects in the Kuiper Belt or on the moons of gas giants such as Neptune and Uranus. Scientists are using the telescope to explore other faraway objects, such Triton, the biggest moon of Neptune, which is likewise believed to contain a subterranean ocean and a geologically active surface. This is because James Webb's discovery of Pluto's hidden secrets has inspired scientists to employ the telescope for research. These discoveries have the potential to transform our knowledge of the outer solar system and offer fresh opportunities for the hunt for life. The possibility that the Kuiper Belt and possibly even the Oort cloud beyond it contain more objects like Pluto, dynamic worlds with complex geologies, atmospheres, and possibly even the conditions necessary for life, is one of the most exciting implications of James Webb's discoveries on Pluto. Pluto is only one of the numerous planets that make up the huge and mainly unexplored Kuiper Belt. Scientists are starting to delve deeper than ever into this far-off frontier thanks to the James Webb's powerful equipment. We may uncover many more shocks as we continue to explore the farthest reaches of the solar system. The findings revealed on Pluto are only the tip of the iceberg. The discoveries made by James Webb have consequences that go beyond our solar system. Pluto's dynamic geology, complicated chemistry, and possible liquid water environment raise the possibility that exoplanets and exomoons in other star systems are going through comparable processes. Other tiny, frozen worlds circling far-off stars may have similar characteristics to Pluto's, which have allowed it to maintain its geological activity and potentially even contain liquid water. Scientists are already using the James Webb Space Telescope to explore exoplanets, and the insights Pluto provided may aid in the interpretation of the data these far-off worlds provide. Specifically, the finding of organic chemicals in Pluto's atmosphere may serve as a model for locating analogous substances on exoplanets, which may be a crucial sign of the possibility of life. Traditionally, Earth-like planets in their stars' habitable zones have been the focus of the hunt for extraterrestrial life. But Pluto's findings are changing that emphasis. If a tiny, frigid globe at the fringe of our solar system can support liquid water and complicated chemistry, then other far-off worlds, even ones that are far from the warmth of their parent stars, may be able to support the same circumstances. Using its cutting-edge equipment to explore the atmospheres and surfaces of exoplanets and exomoons in search of water, organic compounds, and other possible indicators of life, the James Webb Space Telescope is positioned to play a significant role in this mission. Furthermore, the discoveries made on Pluto are compelling scientists to reevaluate existing theories on the creation and development of planets. Pluto's dynamic geology and interior ocean indicate that even tiny bodies may hold onto enough heat to sustain major geological processes. This calls into question the conventional wisdom that only massive planets, with their dense atmospheres and powerful gravitational fields, are capable of sustained geological activity. Pluto is a dwarf planet on the outside of our solar system. If it can sustain this kind of activity, imagine what kind of dynamic other tiny worlds there may be in the cosmos. This implies that we might need to reconsider current planetary science models and has significant ramifications for our comprehension of the evolution of planets and moons. In addition to raising questions about the possibility of life on Pluto, the surprising finding of a subterranean ocean provides important new information about planetary geophysics. It defies conventional wisdom to think that a planet this distant from the Sun could have an interior ocean, which would contradict theories about how planets retain heat and continue to be geologically active for billions of years. Internal heat is sustained on Earth via plate tectonics, radioactive decay, and the effect of a relatively nearby sunday. Considering Pluto's tiny size and distance from the Sun, one would assume that it is geologically dead. The results of James Webb, however, point to the opposite. This has prompted research into potential backup systems that would enable heat retention in these kinds of frigid bodies. Tidal heating brought on by Pluto's and its moon Charon's gravitational interactions is one theory. Because these two bodies are in close orbit, their gravitational pull on one another causes their innards to expand and compress, which may produce enough heat to prevent subterranean waters from freezing over. Although moons like Europa and Enceladus have previously shown signs of this kind of tidal heating, Pluto's evidence of such activity was unexpected. Pluto's liquid water presence suggests that the planet may have unusual geological formations powered by cryovolcanism. When volcanic activity results in the eruption of volatile materials such as water, ammonia, or methane rather than molten rock, it is referred to as cryovolcanism. Pluto's surface may occasionally be altered by the periodic releases of water and other materials from the core of these ice volcanoes. Finding such characteristics would be revolutionary, demonstrating that geological activity can occur on tiny, cold worlds near the solar system's periphery in addition to massive core planets. This suggests that other ice dwarf planets and moons dispersed throughout the Kuiper Belt and beyond may share comparable dynamics. Some of the most puzzling surface features of Pluto, including Sputnik Planitia, a large, heart-shaped plain of nitrogen ice, may become clearer with the assistance of these observations. Few impact craters in this region indicate that it is geologically young, indicating that it has just recently resurfaced. The resurfacing of Pluto may be caused by heated material rising to the surface from the subterranean ocean, regenerating the surface in a manner akin to Earth's mantle plumes, according to some scientists. This creates the intriguing potential that we may be seeing continuing geological processes on Pluto that may still be operating today and that have recently changed the planet's surface. Wide-ranging effects on planetary science will result from the confirmation of these geological processes on Pluto, especially with regard to our comprehension of the evolution of tiny, ice planets. The suggestion is that Pluto is a dynamic entity with continuous geologic and maybe hydrologic activity, rather than a frozen, immobile remnant of the early solar system. These results may indicate that additional objects in the Kuiper Belt, such Haumea, Makemake, and Eris, may also have comparable interior systems, with active geology and subterranean seas concealed behind their frozen exteriors. This theory may ultimately be confirmed or disproved by the James Webb Space Telescope, which has the unmatched capacity to examine these far-off objects. This would result in a significant increase in our understanding of the outer solar system. Not only do these discoveries concerning Pluto have implications for the Kuiper Belt, but they also call into question our understanding of other nearby celestial entities, such the moons of gas giants. Because of the potential implications for alien life, the discovery of interior seas on moons like as Europa, Enceladus, and potentially Ganymede has already created a great deal of interest. Considering that Pluto has been shown to have comparable circumstances, how widespread are these interior oceans across the solar system? Could they be found on additional dwarf planets in the Kuiper Belt or on smaller, less explored moons around Neptune and Uranus? The number of possible habitats for life might be substantially increased by the discovery of internal seas across such a wide range of conditions, suggesting that they may be more common than unusual. The discoveries made by James Webb on Pluto have ramifications not just for planetary geology but also for astrobiology. One of the essential components of life is liquid water, and the hypothesis that Pluto may have a subterranean ocean raises intriguing concerns about whether or not it may be habitable. Pluto's subterranean ocean may have more hospitable circumstances than its surface, which is much too frigid to host life as we know it. Similar to the hydrothermal vents present in Earth's seas, chemical interactions between the water and rocks may provide energy if this ocean is in contact with the planet's rocky core. Even in the absence of sunshine, hydrothermal vents on Earth supply the heat and chemical energy required to sustain complex ecosystems. Numerous species, ranging from bacteria to tube worms, may be found in these habitats and are adapted to survive in harsh conditions. It is possible that microbial life, supported by chemical energy instead of solar radiation, may live in Pluto's subterranean ocean if comparable circumstances are met.